I really apologize to our speaker, Dr. Dewey, for taking up half an hour pre his speak. Dr. Dewey is a physical oceanographer who has lived on and studied the ocean around Vancouver Island for most of his life. Growing up in Victoria, he spent summers cruising through the Salish Sea with his family before university, including degrees in both UVic and UBC. The title tonight is Tidal, Currents, and Kayaks. The presentation will provide an introduction to the theory of tides and what causes the variations on time scales from hour to months. And I had a bunch of questions sent to me about why are tides so high every winter? It seems seasonally, so maybe that's one of the things you can talk about. There will be a brief review of the tide information sources and how to interpret them, which is always very helpful, of course. Finally, we will discuss key aspects of local tides most boaters and kayakers may find familiar with, including tidal fronts, back eddies, and wind-wave tide interactions. We call them standing whitewater. Dr. Dewey. Thank you.
Okay, forward and backwards.
And to get the pointer.
Perfect. Yeah, it's working.
It's working.
Yeah.
Okay.
I've got another one there too. Thank you. Thanks very much. And I gather we could probably have spent the full meeting with the previous team there with questions and answering and figuring out better ways to communicate. So I do appreciate that. This is really a follow-on to a talk I gave at the Yacht Club in November. I'm a member of the Royal Victoria Yacht Club there, and somebody had asked me to talk about tides, so I put a talk together in November. And one of the people in the audience was, I think it was Mike Dixon. Jackson, sorry, Mike Jackson. And he came up afterwards and wanted to talk about a whole list of things. So we decided to meet later that week over coffee, and we probably spent over 2 hours reviewing all sorts of things. And he showed me the apps that he uses, and I've been working since that time, that was in November, on developing a new tidal atlas, which I want to just mention here. So I've added a few slides, unfortunately, to already a long talk. So we'll see how far we get this evening. And just to keep you engaged, I think there's the best stuff is right at the end, I'm afraid. So, okay, so let's get on. This is really, I'll go very quickly through this slide. This is just an outline. Really, we're going to review the theory of tides, so we understand where they come from and their nature and their character. We are going to look at why they vary so much, both in time and in space. We'll just do a quick review on some of the ideas of reading tide tables, making sure we all understand how to read tide tables. They're available from the Canadian Hydrographic Service for free, so there's no excuse not to have one in your computer, be able to plan ahead and so forth. Just talk about the fact that chart datum is related to the lowest low water in Canada. And currents, then I'll talk about specifically about currents, the flood and the ebbs and the shallow flow, deep flow, tidal streams, and now we start getting into some of the things that are more interesting, maybe back eddies around headlands, tidal fronts, and shear. And I'm talking to a group that has experience right down to the smallest scales on the ocean. And you've all been out there on the water. And again, I appreciate that many of you in the room have spent much more time on the water than I have, even though I've grown up sailing in the Salish Sea and working as an oceanographer and now cruising on the Salish Sea. So you're much closer to the water than I am when I go out in a sailboat. And then the last thing I just want to, literally the last slide is this wind against tide. We call it standing waves or rested waves, and you might call it, I think the fellow who introduced me called them something else. So we'll get to that, but that's right at the end. So hopefully we'll stay right through to that. So the moon, the earth, the moon, and the sun all work in symphony, and we can really appreciate Newton, who basically figured out that, okay, we're in orbits, and it's gravity that keeps us in our orbit. And it was the moon he was trying to figure out. The story of him watching an apple fall to the ground, he was really trying to figure out that the moon is there up in the sky, and it's not falling. It just sits there. Apparently stationary, but if you watch it long enough, you know it moves around. And then the apple fell out of the tree, and he suddenly went, of course, it is. Everything falls. So the moon must fall. So the moon is falling. And it's falling in a particular way. It's falling in a balanced orbit. And it's constantly falling. And that's what gives rise to the orbit. And so the tides are a result of the orbit of the Earth and the Moon, and of the Earth-Moon system around the Sun. Both of those are very similar. The orbits are maintained by gravitational forces, which are, of course, attracting the masses, and by centrifugal or inertial forces, which keeps us apart. So when something spins, you want to fly out. So gravity is pulling it in. Spinning things want to pull out, and we have a balance of forces. So they balance at the common center of mass. So I think I can point here on this diagram here. This little dot here is the center of mass of the Earth-Moon system. You can see it's inside the Earth. The Earth is so much larger than the Moon, even though the Moon is quite far away. The center of mass of the Earth-Moon system is inside the Earth, and both the Earth and the Moon rotate around that spot. So if we separate them from the sun, orbiting around the Sun at the moment, and we just imagine the Moon is orbiting around the Earth too is spinning around that center spot. It is not spinning around the center of the Earth. It's rotating around that spot. It's off-center. That's where the forces balance perfectly, and there are no tidal forces at that point only. Everywhere else there are tidal forces. Towards the Moon, you're closer to the Moon. Gravity is proportional to 1 over the r squared, the distance squared. So when you're closer to the Moon, you feel more gravitational force than you do centripetal force away from this center. And on the far side of the Earth, you feel more centripetal force than gravity force. So in this diagram, the red arrows are the forces of gravity, greatly extended in the sense that we're just making them larger differences than they really are. But towards, on the near side to the Moon, the gravity is stronger, and the far side gravity is weaker. Turns out the centripetal force is the same everywhere. We are spinning around. It's much like we just finished the Winter Olympics. The Summer Olympics has this arcane ancient sport where we throw a cannonball on a chain, the hammer throw. And the hammer thrower, when they're spinning around, you can see the hammer thrower, the center of mass may be inside this large athlete, but he's having to spin around as well. And it turns out the centrifugal force everywhere on the planet is the same as we spin around this point. But because gravity is stronger here and weaker here, the net force, the green arrow, is away from the Earth here and towards the Moon there. So we end up with 2 bulges. So this gives rise to why there are 2 high tides in a day and 2 low tides a day, and not one which is just facing the Moon. There are 2 tidal bulges in the ocean associated with the gravitational pull of the Moon. And similarly, the Moon and the Earth system orbit around the Sun. The Sun is much larger than the Moon and the Earth, obviously, but its distance is so great that the Sun's influence is about half that of the Moon. So 2/3 of the tidal force is the Moon, and 1/3 about is from the Sun. But there is a bulge towards the Sun as well. Now, if the Earth wasn't spinning, we'd have one high tide every 14 days. And then 14 days later, we'd have another high tide and a low tide. But the Earth spins underneath these bulges. And the Earth spins, of course, every 24 hours. Without continents blocking the way, we would have ideally 2 high tides and 2 low tides every 24 hours as the Earth spins underneath this tide bulge. That's the really sort of an interesting point. The bulges do not follow the Moon, or aren't a result, getting ahead of myself here. So some people think, well, I got the Moon straight above, but I've got a low tide. Shouldn't the Moon be pulling the water up? So I should always see high tide when the Moon is above. All right? The high tide is facing the Moon. The Earth is spinning around underneath it. All right? So the high tide does sort of face the Moon, but the Earth spins around underneath. Because we have continents blocking the wave doesn't travel around every 24 hours like that. It gets blocked by the continents. So I think I said everything on this slide. I'll move on to the next one. The continents turn out to be incredibly important. The moon's orbit surrounds the Earth once every 28 days, and the Earth around the sun, obviously 365. Underneath these satellite-aligned bulges, the Earth spins on its axis every 24 hours, giving rise to the daily tides, or actually semi-diurnal tides, twice a day for the moon and the sun. Without a tilted axis, the continents, the tides would be relatively simple and similar everywhere on the globe. But the Earth is tilted. We're going to see what causes that. We actually had a question coming up, and I'll address that in particular. Because the Earth is tilted, we have seasons, and we have seasons in the tides as well. The Earth is tilted at 23 degrees relative to the solar plane, the ecliptic, and the moon's orbit is tilted at 5 degrees from the ecliptic, and that varies. That varies on long time scales. So the moon is above the ecliptic and below the ecliptic on various time scales as well. And that gives rise to some of the longest variability. The longest variability in the tides is about 19 years. So there's actually, there's daily variations, monthly variations, seasonal variations, and the longest variation that we can possibly measure is about 19 years, and that's due to all the variations in the alignment of the ellipses. The continents in particular interrupt these bulges, and they interrupt them in rather interesting ways. So here we have on this flattened out map of the Earth here. And in particular, you can imagine if the bulge was at the equator, ideally it wants to propagate around the globe, along the equator. But here's North and South America providing a complete blockage to that bulge wave that wants to propagate around the world. It cannot propagate around the world. It hits the continents, and it gets broken up into lots of little, I'll call them seiches. So if I had a wine glass here, at the Yacht Club, somebody came up and gave me a wine glass. That was great. A seiche, if I sit there and spin the wine glass, I set up a seiche in that wine glass. Okay, so when I'm talking about a seiche in a basin, it's basically a wave that propagates around an enclosed basin. All right, the ocean, some of the basins are enclosed, but the Pacific Ocean in particular is actually too large to have one seiche, and it has lots of little seiches. The tide gets broken up into lots of little seiches, and each one of these nodes is where one of the seiches spins around. And in the North Pacific, we have a node right off here, off of Baja, Mexico, and it propagates, the tidal wave propagates counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. And the reason for this is because Coriolis wants to push things to the right in the northern hemisphere, things to the left in the southern hemisphere, and the boundaries then always end up on one particular side of the wave. So in the northern hemisphere, the wave that's propagating up the coast here actually wants to turn to the right. The coast prevents it from turning to the right and provides, if you like, a sort of a wave guide, and it forces the tide to propagate around here. It propagates around this nodal point once every 12 hours for the M2 tides, the S2 tides as well. And I think we can go on to the next slide, or the next diagram here. So here I've zoomed in a little bit on our coast. These phase lines, we're going to circulate around in an entire circle once every 12 hours. Each one of these phase lines is 20 degrees, which is about 40 minutes. So from Baja, California, every 40 minutes, the peak of the tide, the high tide, propagates up the coast. It goes down the Aleutians, and then it quickly jumps almost all the way across the Pacific. Now, the tide height out here is very, very small, but it's deep water, so it doesn't have to move much water. The tide height as you get up the coast, and in fact, as you get to the Gulf of Alaska, we get it, as the previous slide showed, the red part, the color, is the amplitude. So we see in the Gulf of Alaska, we have relatively high tides all the way up our coast. Very low amplitude tides out here, some off of California. There are other places in the world where you have very high tides. Bay of Fundy, you'll note, doesn't necessarily have a large tide. Its tides are large because it's in resonance. I'll talk about that shortly as well. Here's off the Bay of Biscay in England. They have very large tides. And there are other places in the world where you have large tides. There are many places, coastal areas, where you have very, very weak tidal height variation. And it's just the fact that the base size and shape of the ocean basins determines the character of these tidal seiches. That's why the tides vary everywhere and differently around the world. They have the same sort of character, 12 hours, 24 hours, monthly, fortnightly, and so forth. Some areas the tides are weak, and some areas the tides are very strong. Obviously, we're up here, our entire BC coast, all the way up to Alaska, relatively high tides. So the tidal height travels up the coast here. You'll notice that along Vancouver Island, the high tide would be off of Oregon, 40 minutes later off of, there's Brooks Peninsula off the west coast, 40 minutes later up in Haida Gwaii. That's how fast the high tide's propagating up the coast. It's relatively quickly. We would experience pretty much the length of Vancouver Island, high tide within half an hour of its, everywhere would see high tide within about half an hour of itself, okay? So the whole Pacific coast is going up more or less at the same time. It is propagating up the coast, but it's not propagating up slow enough that you'd see, oh, an hour difference or 2 hours difference between here and Cape Scott. The whole propagation is going to take maybe less than half an hour or so to propagate up the coast. So that's how the tides propagate up our coast, and we do have large tides off our coast. Let's talk about some of the other variations we're going to see. At mid-latitudes like Victoria, the tilt on the Earth's axis introduces seasonal variations. And there's going to come to this question we've already just had. Oh, I think going back, and I won't go back on the slides, but, well, maybe I will just because I can. This one shows that when with the moon and the sun are aligned, the two bulges align, and we have the highest tides of the month. They're called spring tides. And when the moon and the sun's bulges are at quadrature, or opposing each other, that's when we get neap tides. And since the moon goes from a new moon to a full moon in 14 days, we go through a spring tide, neap tide, and back to a spring tide in 14 days. And we kept all the way around back to a new moon in 28 days. So that gives rise to the spring neap cycle. And the spring neap cycle is when the sun's and the moon's tides are aligned, and neap tides is when they're at quadrature. Okay. Now let's talk about other variations. This is a little diagram I've shown here, and I've tried to put a mid-latitude line here, and maybe even somebody standing on the moon at this mid-latitude. And because we're tilted at 23 degrees, we get seasonal variations. So if this is us here in Victoria, and I think this is probably lower latitude than Victoria, it's probably something like in California or Mexico. Nonetheless, the sun's tidal bulges are along this ecliptic, all right? In the winter, and we're in winter now, our North Pole is facing away from the sun, and so the tidal bulges are going to be here and here. And in the summer, the tidal bulges are going to be here and here. I've put this person here at noon, basically facing the sun. You'll notice that the tidal bulge for us is going to be maximal at night here and daytime here. We get a 12-hour shift in the maximal tides due to the sun at our latitude because of the tilt of the Earth. Now that doesn't mean that we're going to see it exactly like this, because again it propagates up our coast. It may be out of phase a little bit, but I've drawn here the tidal for, I think it's the tidal heights for Victoria. This was last year, 2025. For the entire year, we can see some of the seasonal variability. The spring neap cycles are these weaker tides, stronger tides, weaker tides, stronger tides, weaker tides, stronger tides. That's the spring neap cycle. And here we have when the sun's bulges start to align with us in our winter, and they align with us in our summer. The low tides happen at noon in the summer, and at noon, the high tides happen at noon in the winter, just because of that tilt and the way the sun's bulges align with us different because we're on a tilted planet and the sun. So there's the seasonal aspect to the tides. So in our summer, we get our lowest tides at noon. So most of us go sailing and kayaking or cruising in the summer. We get our lowest tides around Victoria in the summer, right at noon. And in the winter, we have our highest tides around noon. And this is when also we get the storm surge conditions. We also have a pressure effect due to atmospheric pressure. When there's a low pressure, it doesn't weigh down on the ocean as much and allows the ocean to rebound up. So you can imagine a low pressure is also, you can imagine we call it a ridge as a high pressure and a trough as a low pressure. The pressure you can think of as the thickness of the atmosphere. The atmospheric pressure at the surface of the Earth is the weight of the air above us, And when we're in a trough, we're in a low part of the atmosphere is thin, and we get low pressure. When we're in a ridge, or we have a deep atmosphere, we get high pressure. So in the winter, when we have a storm coming through, we get most of our low pressures in the winter. So we have a thin atmosphere going over us. It allows the ocean to push back a little bit. The ocean actually rebounds. It's not under so much weight under the atmosphere, and it pushes back. And so that you get higher tides under a low pressure. In the summer, we get high pressures. It's going to push down on the ocean a little bit, and you're going to get your lower tides in the summer. So you get really high tides in the winter, really low tides in the summer. I'll also note on this chart, and I'll come back to this a bit later, this is the chart datum here, 0, and we can see during the summer at these low tides, we're actually below chart datum, and the low tides in the winter sometimes are also below chart datum, but I'm getting a little bit ahead of myself there. Let's talk about just some common terminologies. Tidal heights, obviously a rising tide is the time it's heading towards a high tide. So water is flowing in from the Pacific. This is another thing it's really fairly obvious. The tide is being driven by a wave propagating up the west coast of Vancouver Island. Everything else is responding to that wave, that tidal height variation off the west coast. You get a high and then it's a low. And the inside water and the Salish Sea is responding entirely to what's happening off the west coast of Vancouver Island through either Wandefique Strait or Johnson Strait up around Cape Scott, the northern end as well. So the water's going up and down there, and the whole rest of the Salish Sea is just responding to that. So when it goes high offshore, it wants to flow in, and it fills up the inside basin, and then it drops out, then it drops out in Vancouver Island, and the water has to flow out of the Salish Sea. Then the tide increases off the west coast, and it flows back into the Salish Sea. It's always the forcing from the Pacific driving the rest of the system. Falling tide, it's heading towards a low tide. Tidal currents, flooding is when it's heading towards a high tide. Flooding, although we'll look at a chart, you can find places that are very convoluted. Water's coming in from the Pacific into areas further inshore. Now you can imagine there are places where the tides get complicated around islands, and I'm going to show you one place where it goes in the same direction, both flood and ebb. But nonetheless, you can think of flooding, it's coming in from the Pacific, ebbing, water's heading out to the Pacific. It's a general rule of thought. Currents and heights are almost completely out of phase in most places. So it's flooding, and then when it gets to the top, it's slack tide, and when it's peak ebb, it's when it's dropping. So if you look at curves of currents versus tidal height, they should almost be 90 degrees out of phase. Spring neap, that's when a new and full moon, the sun and the moon's bulges are aligned. Neap tides at first and third quarter. Semi-diurnal and semi-diurnal, maybe terms I'm throwing around. Diurnal means at times you can get tides that are dominated by one high tide and one low tide during a day. I'll show you an example of that. Even though both the moon and the sun are driving semi-diurnal tides. Both of those stations want to go into semi-diurnal tide. They get a little bit out of phase and they add and subtract from each other. So at times those variations are weaker, and at times they're aligned at spring tides, their maximum. And in some places like Victoria, you can end up with diurnal tides. Show that in a second. So we have daily tides, which are diurnal, or twice a day tides, which is semi-diurnal. To read tides, you go to the tide tables. This is for, I think I pulled up the 2025. You can go to the Canadian Hydrographic Service. They have the tides, the website there, tides.gc.ca. And for the West Coast, there's a number of volumes. This is volume 5. It covers all this area in the lower part of the Salish Sea here. And all of these stations are either current or height stations. And in the tide tables, there'll be the tide tables reporting for the next year. One thing to point out with the Canadian Hydrographic tides, they're always in Pacific Standard Time. So even in the summer when we have daylight savings, you've got to be adding an hour to get daylight savings time. So this one, I originally gave this talk. I didn't redo this. I gave a talk in November, but there's a good reason for that, because in November I had some interesting tides in Victoria. So this is what we're all familiar with. This is what a tide table looks like. Let's zoom in on the 18th. This is the 18th of November. It's showing us the time of a high tide, time of low tide, time of the next high tide, time of the next low tide in both meters and in feet. This is Victoria, and we'll see that there's a high tide of 2.4 meters, a low tide of 2.3 meters, so a tenth of a meter, then another high tide of 2.7, and then a really low tide, one low tide, and it looks like one large high tide. So if you look at, and this is also from the tide tables, they've plotted up for some of the stations, they plot them up as time series. And you can see that in Victoria, which is a particularly strange place because we're at the if you like, the axis of the seesaw. So the Pacific Ocean is going up and down, the Salish Sea and the Strait of Georgia is going up and down, and here's Victoria right in the middle. So the tide's going to be doing some funny things in Victoria. Not only is it tilting like this, it's going up and down. So you can imagine where my finger is at the end is extreme. The Pacific's going up and down nice and uniformly. Maybe at Point Atkinson it's going up and down quite uniformly. But in between it's doing some pretty funky things. It's getting wiggled all over the place, and that's Victoria. Later in the month of November, here we have a condition. We have a very low tide, again happening at midnight, and one large high tide all day long, and then a short low tide at night. So here we have this diurnal nature, and other times during the month, it's sort of mixed or semi-diurnal. And I've put on here the phases of moons. We have a full moon, third quarter, new moon, first quarter, as it progresses through the 28-day cycle on a month. So what's actually happening here, and I think I had the tide tables I had for the 18th, it shows a tide coming up, then a very small change, and another high tide, and then a big low tide, with a very small change here. That's the tidal height. The currents may be doing something quite different. Now I'm looking at the tide tables for currents, and there they display slightly different information, but again, always in Pacific Standard Time. And now let's zoom in on November 18th again. And this is showing when we have the peak. This is the time of the peak currents. Here's the peak currents, and here's the approximate time of slack tides. So we have a flood tide, which is a plus tide. That means it's coming in from the Pacific Ocean. Most places, it's fairly clear which is the Pacific side and which is the inland side. So somewhere like Race Passage, Active Pass, most of the major passes, it's fairly, Seymour Narrows, it's fairly obvious which side is Pacific and which side is inside. Other passages, not necessarily so often. They may be inside an island and so forth, but there'll be one of the directions will be flood and the other direction will be ebb. So even though the tidal variation we saw in the height at Victoria was only about 10 centimeters, all right, the currents at Race Rocks show fairly uniform. They, in fact, show a fairly strong 5-knot current flooding, 3.5 knots ebb, 2.5 knots flooding again. So even though the tidal height at Victoria was almost diurnal, the currents remain semi-diurnal. So currents are actually more important to read than tidal heights. Tidal heights are really good for when you're anchoring, when you're going to the beach, when you want to know how much beach I have or how much clearance under the boat I have or whether a passage is accessible if it's a shallow one. But for the currents, you really want to go to one of the current sites. Victoria is particularly sort of troublesome. You can't look at the tidal heights and get a good idea of what the currents are happening. Fortunately, we have this current station. I use Race Rocks regularly as my primary for the southern part of the Salish Sea primary station. It turns here first, which I'll talk about in a second as well, and it gives me a best idea of what the currents are going to do throughout the whole Gulf Island area. So in addition to these tide tables that the Canadian Hydrographic Service puts out, there are many tidal apps that are out there, phone apps, lots of weather apps now have tide stations in them. Navionics, if you're using for navigation, it'll have tide stations in there as well. This is an old one I had from called X-Tide or WinX-Tide. It's relatively old in the sense that I think the version I have is from 2004. Which means it's using relatively old tidal information, but it's fairly good. This is for the 18th. This is November 18th, the same day we were looking at before. It has a strong ebb, a flood, an ebb, and then a large flood the next night. It's in November, so we have a long nighttime and short daytime. And I know it's very hard to see, but these are the times of this is the time of maximum flood and maximum ebb here. So floods are in blue. And they're very similar to these times, but they're not exact. They're off by plus or minus 5 or 10 minutes. And this will be the case in almost all the apps you have. Very often you'll have downloaded the app and it will be using an old set of harmonics to reconstruct the tides. They're probably very, very good, but the Canadian hydrographic tide tables are updated with new harmonics every year. So this tide tables you get from the Canadian Hydrographic Service is going to be your principal reference. These times you get from the other tidal apps you can get on the web and websites and even things like Windy and Navionics. They're going to be using old harmonics, and the times may vary by as much as 5 or 10 minutes. For most of us, that's not too much of a problem, okay, 5 or 10 minutes. But just be aware, you'll see some mismatch between the times that these charts give you and the apps versus the Canadian Hydrographic Service. So while we're talking about apps, after I gave this talk at the Yacht Club, I had coffee with Mike, and he showed me that he uses on his phone an app that pulls up the old Juan de Fuca Current Atlas. And it pulled up maps, and it had a time on it. It goes through real time right now, and it pulled up a map of the currents from the old tidal atlas. I think there was a version up on the table there, I noticed. That was a model that was developed in the 1970s by a fellow called Pat Crean, and those maps were generated back in about late 1970s. And Mike and I said, well, I have a tidal model accessible to me that I run, and I do current maps for Swiftshore. It's more recent than that. It's not brand new. It's maybe 20 years old, but it's much higher resolution. Covers the entire coast of Vancouver Island. And Mike convinced me to go ahead and start working at updating a current atlas. So this past winter, I have a model that would generate these sort of current maps. I got them. Much higher resolution. I think in the original one it had like one arrow here, and maybe. So this has resolution of down to several hundred meters or less. And this is just a tidal atlas. We know where we are. Here's Trial Island, discovering Chatham, Bain Sound, coming through Oak Bay, around the waterfront of Victoria. And so Mike convinced me. I said, my model produces much higher resolution, and it covers the whole area around Vancouver Island. So I'm now working on volumes 1, 2, 3, 4, and 5. I've already published volume 1, 2, and 3. It's available at my website, dewey.ca. And this is the first time I've had a chance to announce it. I just put it out there over the last month or so. And I'd certainly like, if anyone has the time, it's based on the old current atlas, which is a really clumsy way. It generates maps, and then you have a lookup table. And you go to the lookup table and it says, okay, for this time, anytime during the year, I want to look at map 34, and you go to that page, and it's a map showing the currents that will be similar to that in that time. And I haven't generated, I'm working on volume 4 and 5, but they'll take a few more months to generate. And like I said, it's at my website. I haven't done much promotion. You're the first audience that has really heard about it. So,
question?
Yeah.
On the map, can you go back to the other side?
Yep.
Okay. That looks like a flood tide to me, but the water running through Oak Bay, through Baines Channel, is going south.
So this is beginning of an ebb tide. So it's still flooding out here, and I'm going to talk about that in a second. In deep water, the tides don't slow down by friction. They have to run uphill. So if I imagine I had a block of wood here, let me use a 2x4 or whatever, and I was careful enough to balance a bowling ball on it. I tip the wood. The surface of the ocean is what gives rise to the tide. The tide's always trying to run downhill. So if I got a slope in the surface of the ocean, it's always trying to run downhill. Underneath the deep water, it's high pressure. Underneath the low water, it's low pressure. So the pressure is always pushing downslope. When I'm in deep water, imagine a bowling ball on a piece of wood. And I tip the surface, and the bowling ball starts to roll downhill. And I tip it the other way. For a while, it's going to roll uphill before it stops. And then it's going to roll downhill, and I tip it, and it rolls uphill for a while. In deep water, out in Harrow Strait, out off Victoria and Juan de Fuca Strait, that's deep water. It doesn't feel the bottom. It's going to roll uphill before it turns around. And so the surface slope is flipped. Race rocks, it's turbulent, it stops right away and flips right away. So race rocks turns about an hour sooner than off at there's a current station off at Juan de Fuca East there out in deep water. It turns about an hour later than at race rocks. And race rocks is turbulent and slows down. So turbulence is if I had a bowling ball that was now covered in something fuzzy, let's say even Velcro material, and I had Velcro on my board. And so turbulence is always trying to slow it down. Doesn't matter which way it's going, but turbulence is slowing it down. When I tip the board, it stops right away and starts rolling back the other way. So turbulence acts to slow things down. Always, whatever direction it's going is trying to slow you down. And in race passage, it's so turbulent there that it turns, as soon as this slope turns, the turbulence dissipates the momentum, if you like, in the flow, and it responds to that pressure gradient. And you can get a tidal difference between, again, out here in deep water in Harris Strait. Come on. He says. In Harris Strait, you can see it's still flooding, but it's ebbing already through a bay in the shallow passages where it's turbulent. So I'm going to go quickly through this. Summary of the tides. I think we've seen all this stuff before. I think there's this point I've just made here. Tides are slowed in shallow water. They turn and reverse quickly, while tidal currents in deep water are slowed by flowing uphill before they turn and reverse, as much as an hour later than in shallow water. So race passage turns an hour before it does at Juan de Fuca East. So if you're in the boundary layer, most of your kayaking, a lot of our boating is happening in the boundary layer. I look at race rocks. I know that's a good time for when it's going to be turning in Oak Bay. It turns first at race rocks. It's going to turn first through Baines Sound, Baines Channel. It's going to turn first in all of the shallow channels. Going to keep moving on here. As far as charts are concerned, in Canada we use the tide table as a reference to low water, large tides, which means Canada looks at the largest tides of the year over a long period and basically says that's going to be our chart datum, it's going to be 0. A few times during the year, we saw that previous plot, it's going to be below the chart datum, maybe half a dozen or so tide cycles, just below chart datum. When you have an app and it says you've got 6 feet of water, that's 6 feet above the depth that the chart is reporting. The chart is always reporting the depth at basically the lowest tides that are expected for the year, and some very low tides are below chart datum, so be aware of that. In the United States, they use mean low or low water, which is a little bit higher than the Canadian standard. So there's a slight difference on the US charts if you're navigating through US waters, the NOAA charts. And I think I've already mentioned that you can have high and low atmospheric pressures that gives rise to additional tidal variation. And again, under low tides, under low atmospheric pressure, the ocean can push back against the atmosphere. Or if you like, the atmosphere doesn't push down so much on the ocean, and the ocean rebounds a little bit. You get slightly higher tides under low pressure, slightly lower tides under high pressure. You can also get persistent winds that pile water up. So let's talk about some of the more interesting things as far as boating and kayaking is concerned, tidal currents. I originally put this together for sailors, but when you're out there racing and sailing, you want to avoid bucking the tide. And by that, I mean if I'm trying to get somewhere that is dead into the current, I'm better to go to the boundary layer where there may be turbulence and the current's slower, rather than sit out here paddling away in the strongest current. I need to find somewhere where the current is weaker. And as you know, the currents vary on all sorts of timescales. Even the diagram I had there showing nice smooth patterns. There are small places where the currents are weaker behind every Fiddle Rock, every Todd Rock there, and Fiddle Reef. They have back eddies behind them, even though they're tiny rocks. You can find under a flood tide, you can get behind Fiddle Reef, and you can get sucked right into Fiddle Reef. So the model there is hundreds of meters resolution. To resolve those sort of scales, we need to get down to 10 or 5 or even 1 meter scales. Those sort of models are impractical to run. So that'll never happen. We'll never have that sort of scale of resolution of models. There's almost no point to it. But that's the scale at which we experience, and certainly in a kayak. So behind every rock and every island, there's going to be a wake. There may be a back eddy. So you want to get out of a strong tidal stream as soon as you can. You don't want to spend a lot of time paddling. You're just wasting energy and wasting time. Now, you may be just an exercise. I'm going to go out there and I'm going to paddle in the side. I'm not going to go anywhere. I don't want to go anywhere. I want to get back to my car. That's fine. But if you're trying to get somewhere, get out of the tidal stream and find a place where the currents are weaker and then paddle in the stream. So tidal currents are driven by the surface slope. I think I mentioned that before. Tidal flows around islands and headlands are blocked by the islands, and they result in two things: back eddies and wakes and jets going around them. So we have in this diagram here, and I pulled this off of a website by a fellow called Rich Brown, and I've gone back there and the website's been taken down because they think he's published a book. And it's a book specifically for sea kayaking, and he talks about tides. But I managed to pull this figure off his website before he pulled the website. But it shows basically you have a tidal stream here and you have a headland, and the tides may be uniform out here, but it's going to get compressed going around this headline. And you can think of the speed is increasing where the lines are close together. So as all this water over here has to get by here, it compresses, and you get a real tidal stream here. All right? There will be a back eddy here. We only have to look at this headland and know there's going to be a back eddy here. First of all, the water shooting out here at great velocity is going to suck water out of the corner here. And so you end up with this back eddy. And so if I were paddling along this coast, don't paddle along out here. Come in here, know there's going to be a back eddy, even though this is where I want to get to. And you think, oh, the shortest course is along here. The best course would be to get in here and find the back eddy. Now, when you get to the point here, you're going to have to do some work. You're going to have to get through part of the tidal stream, but you want to get out of that as soon as you can. Losing my button there. Got a little one here. So you want to try to get out of that and get back into coast. Now, there could be all sorts of tidal eddies and sheds all closer here, but you don't want to sit out here in the main stream bucking it as you come all the way along. So that was the key thing for sailors and kayakers as well. Then I had a point here at the bottom for sailors only, is that when you're sailing, you've got wind in your sails, which is your engine, and wherever you can, you want to put the tidal current under your lee bow. So if the sailboat's leaning over this way, you want the tidal current under your lee bow. First of all, if you're beating, you're trying to get in that direction, so the tide's going to push you in that direction. The other thing, by the tide pushing in this direction, it puts more pressure on your sails, which makes you go faster. If you put the tidal current on your windward bow, okay, it's pushing you away from where you want to go, and it's reducing the pressure on your sails, so you go slower. So wherever you can, and sometimes you just have to eat it, you're going to have to get in the stream, you're going to have to cross it as fast as you can, but wherever you can, you want to put the tidal current under the lee of your bow. The other place that tides get compressed is when they have to go over a shallow reef. And now they're being compressed not laterally, but vertically. And you can have deep water and then shallow water, and all of this water is getting pushed by a surface slope up here, and it's going to rip over this shallow bank. And we have lots of that in British Columbia as well. So I was looking for some pictures of, I want to talk about tidal fronts, and I found this is just a picture I took from a seaplane heading to Seattle maybe 20 years ago. And I was looking back, and again, we recognized where we are. Most of you already know where we are. Here's Trial Island. Here's Oak Bay. Here's Caddy Bay. Here's Chatham and Discovery. We're looking out into Harris Strait. Here's Darcy, and here's Sydney Island, so for example. And I can look at this picture, as many of you probably can, and know what the state of the tide is. It's flooding. The current's coming along here. Oh, come on, now I got to get this one to work. Did I turn it off? No, I don't know if I turned it off. Oh, I did. I think I've turned it off. Where's the battery dead?
I have extra batteries.
Do you? We'll manage. So the current's flowing along here. It's bumping into Trial Island, and this is a wake pattern. So I would look at this and I think, thank you. I look at this and say, this is a wake pattern. It's in the wake of the island, therefore the current must be flowing in this direction. The water's piling up here and jetting past Trial Island. The currents are going to be weaker in here and stronger out here. So I have a tidal shear front right along here that I should be aware of. If I'm heading in this direction, I may want to get close to it. It's going to be the strongest current in the region. If I'm heading westward, I want to avoid that, like the plague. I want to run up as fast as best as I can in the wake and get through. The tide might be flooding through Enterprise Channel here, maybe in Baines Channel as well, but I want to come up as best I can in the wake and then get through here as best I can. I'm looking for back eddies and wakes when I'm going against the tide. And when I'm going with the tide, if I want to rush, I'm looking for the streams and I want to ride them as best I can. Page down, here we go, let's try this. So this is obviously a very familiar area. We are in Victoria. Here's the San Juan and Gulf Islands. This is the region between the Pacific Ocean coming in through One-Fifth Strait and the Strait of Georgia. Strait of Georgia is over 300 meters deep. One-Fifth Strait's 200 to 300 meters deep. Deep regions, lots of water to move around. The water in the Strait of Georgia, we've got to raise it 10 or 12 feet every 6 hours. That's a lot of water that has to pass through this region. So we have some of the most complicated tidal current patterns, I wouldn't say in the world, but certainly a complicated area. Each one of these little headlands is going to have a back eddy or some current structure around it. Every shoal is going to have some sort of acceleration or some feature to be aware of. And no model is going to be able to predict all of those, but you guys will know what to look for. So if I just go page down, I want to zoom in a little bit on this area up here. This is off East Point on Saturna Island, Boundary Pass here, Patos Island here. And this has got quite a few of the features that I've already been talking about. This is showing a flood tide. I can look at this, and without actually seeing a model or having been there, I already know what to expect, as many of you will. I would expect under a flood tide, there's going to be a back eddy behind the island here, no doubt. There's a shallow bank that extends over here. 250 meters here, 50 meters here. This water is going to be compressed over. Some of it's going to try to go around, but a lot of it has got so much inertia and momentum, it's going to come and ride up the slope and go over this shallow bank. There's going to be very strong currents going over this bank. I've got 250 meters of water moving quite quickly. That water has to go through a 50-meter pipe, if you like. From 250 meters, a compression of 5 to 1. So the currents are going to be 5 times stronger here than they are here. And the currents are already strong here. So just by looking at the chart, I can get an idea of what the currents are going to be like. Not only is there going to be a back eddy here, but the currents are so strong here, they suck the water out of Tumbo Channel here under a flood. And then under an ebb, they push the water this way. The ebb current also goes through Tumbo Channel to the south. So here's a place where the currents in Tumbo Channel are always flowing this direction. Under a flood, they get sucked out because the currents are so strong here. The water gets pulled out. It's like a big back eddy, if you like, circulating this way. And under an ebb tide, it gets pushed from behind and flows out this way as well. So there are places where the tides don't reverse because of back eddies and sharp topography changes. Sometimes you just have to know, okay, that's the characteristic. But in fact, if I look at this long enough, maybe I could have figured that out. That this flood tide is not going to be able to turn. It's a huge amount of momentum. This is 250 or 100 meters of water here. It's not going to have enough momentum to turn and go up Tumbo Channel. There's no way that amount of water, that mass, is turning 180 degrees and going back up Tumbo Channel. It's actually going to continue to straight on, and it's sucking like a vacuum. It's going to suck the water through on the flood tide and then get pushed from behind on an ebb tide. So maybe I could have even figured that out without knowing that. But there are going to be local characteristics that if you've been there, then you know what to look for. I've got this in there that we've already seen this as well. This is an older map of the same model I have. Again, showing that a model like this cannot reproduce all the features that are out there. I've already talked about it, Fiddle and Todd Rock, for example. There's going to be back eddies where the currents, and this one is an ebb tide in here. There's going to be wakes behind each of these islands. This model has no hope of reproducing those sort of small features. But they are the features you experience in a kayak. So look at the charts, know the general patterns, and then you just need to think, okay, there's a sharp edge here, there's an island, there's going to be blocking, there's a sharp cutoff, there's going to be a jet coming off of the back of this one. So you can just look at a chart and figure it out. I put this in, this is just showing the very general patterns of tides on a large scale. This is a flood tide into the Salish Sea. It's coming in from the north side. Johnson Strait puts in very strong currents, but not a lot of volume. The tides meet about here sort of halfway up Texada Island. The tide's in from the Pacific, from the south side, and the tide's in from the Pacific on the north side. So they're much further north. So we've got to fill all of this strait from the Juan de Fuca Strait. That's why the currents are so strong down here. And here we have the chaos happening through the Gulf Islands. And then here's the ebb tides going back out. Again, there's almost no current here. Lots of tidal height variation, but not much current, because we're sort of at the end of the bay. Captain Vancouver, I think he was about here at Saturna when he realized that it's an island that he's going around. Because if it was a basin, the currents would have been behaving very differently. And he saw the current started to weaken here, and he realized, oh, there must be a northern entrance to this basin here. This is not an end basin. This is not behaving like an inlet. It's behaving like an island. Now, he knew a lot about the tides, and they would ride the tides in, anchor, and then ride the next tides in, certainly. And so he knew by the time he was about here, I think sort of around this area, that it was an island before he even got all the way around. Okay, tidal mixing. I've added a few slides here, and I know we're running really late, but I just want to...
We got till 9 o'clock.
I know you guys got till 9 o'clock, but I do want to leave some time for questions as well. I put this one in because it's a lead up to tidal fronts. When you're out there on a kayak and you come across a tidal front, what's causing the tidal front? Tidal fronts could be like a collection of seaweed, a collection of logs. It could actually be a shear front like we saw off Trial Island. But to get a tidal front, which is collecting seaweed in bubbles, you need to think about mixing. And what happens with strong mixing is, or when you get currents going around headlands and over bumps and around rocks, you get a lot of mixing. And turbulence can be localized and is typically very localized, and it's the eddies and the vertical mixing that we see. Turbulent mixing is an irreversible process. I can put cream in my coffee, and for a while there, it looks like they're separated, but if I stir it, they're fully mixed. There's no way to unmix mixed water. You can, if you're very careful in stirring, you can actually stir different fluids and almost unstir them. And mixing only happens sort of a molecular level. Once you get turbulence involved, it's irreversible. So when water masses, the ocean is stratified, and when you mix a stratified environment, you're mixing lighter water down from the surface and downwards, and denser water upwards. And that's what gives rise to tidal fronts. And I've got a couple more slides here. So mixing at the ocean surface, there we are in our kayak or our boat. It always brings colder, saltier, denser water from depths up to the surface. At the same time, it's pushing down warmer, fresher, less dense water downwards. But the consequence of that mixing is the surface water always gets denser. Because there's no water above the surface, it's by definition the lightest part of the ocean. If there was any lighter part, it would float there. So by definition, the lightest part of the ocean is always right at the surface. And when we mix from below, we're always mixing in dense water. So when it's mixed, it becomes denser. Does that make sense? I got a point at the bottom there. As an oceanographer, it's interesting. At the bottom of the ocean, the opposite happens. The densest water is always right at the bottom. And when I have mixing at the bottom of the ocean, I'm always mixing down less dense water. And the mixed layer at the bottom of the ocean is always a bit lighter than an unmixed bottom boundary layer. At the surface layer of the ocean, that mixed layer is always a bit denser than if it wasn't mixed. Now, I've added a few slides here, and I don't know how visible they are. This is my own data from over 20 years ago. And this is showing, I don't know if you can see the map here. This is Cape Flattery, Vancouver Island. This is a station I established right at the entrance to Juan de Fuca Strait. And I'm lowering through the water column an instrument that's measuring the temperature, the salinity, and the pressure. And from those three parameters, I can calculate the water density. And what I'm plotting here in red is the temperature profile. It's cold at the bottom, and it gets warmer right at the surface. Green is the salinity. It's fresher at the surface, and it gets saltier all the way to the bottom. And blue is the subsequent density. Cold water is denser, salty water is denser. Both contribute to stable stratification, we'll call that, which is dense water at the bottom and light water at the surface. It's hard to see the numbers here, but we have the deepest water coming in Juan de Fuca Strait here is about 6 degrees. It's cold. This is a profile from late June, I think, in the middle of the summer, but it's really cold water coming into the Juan de Fuca Strait. Surface water is about 13 degrees. Salinity at the bottom of the entrance to Juan de Fuca Strait is about 34 parts per thousand. All right? And now we've gone up into the Strait of Georgia, near the mouth of the Fraser River, and we see the profile is quite a bit different. Temperatures are now 9 degrees at the bottom. Depths here is still about 300 meters. This is about 300 meters. 9 degrees now at the bottom, quite a bit warmer. It's quite a bit fresher, about 30 parts per thousand, whereas the bottom out here is 34 parts per thousand. So we've managed to freshen this water somehow. We've managed to warm this water somehow, and it's warmed when it's passing through the Gulf Islands. We've mixed top to bottom. It's re-stratified itself, but we've got some of the surface heat all the way to the bottom here. And we've got some of the surface salinity all the way to the bottom here as well. It's not pure oceanic water anymore. It's been mixed. And if I look at a station in between, and this is a really strange one. This is an amazing bit of observation. Here we have the station, and you can see where we are. Here again is Oak Bay. This is San Juan Island. Here we are in Harris Strait. And we were out in Harris Strait sampling in various phases of the tide. And this one particular time, I think we were on the Vector, the Canadian hydrographic vessel Vector, as opposed to the Tully a few years later. And we were in a huge boil. Now, as a kayaker, you know what a boil is. It's where the water's coming up from below. And usually what's happening there is the water's running along the bottom and it runs into an obstruction deep at the bottom. It gets shot up to the surface and its momentum comes all the way to the surface and it sort of boils up. And you see this calm, circular, usually circular in some sorts because it's coming up in a jet and it's boiling up. I would call it a boil. I don't know if you guys have a name for it. And it boils up and it's sort of calm and it's pushing, it's moving away from the center, okay? And it's pushing all the waves out to the outside. And then where that water sort of actually starts to come down, you get a sort of a rough area right around the perimeter. And we were in a boil here that was 300 meters deep. So the water's coming along the bottom, it's hitting some ridge at the bottom, and we looked at the charts, it wasn't even obvious. Now it's getting advected by I think we were in a flood tide, so we had to look upstream to where the bumps were. We were in a boil that was 300 meters deep. So 900 feet of vertical water all coming up at the surface here. And the temperature is uniform, top to bottom. Salinity, uniform, top to bottom. Density, uniform, top to bottom. It is thoroughly mixed. It's 300, where usually now, half an hour later, the tide slackens off. We went back here. We couldn't find this vertical proof. We found water of this temperature. 9 degrees. We found water of this density, and we found water of the salinity. But it re-stratifies. It pancakes out into its depth, wherever the density is, rather quickly. It was very surprising. But at times you get this vertical mixing. So I just wanted to point out that the tidal mixing causes everything to get mixed uniformly. Okay. So when mixed water meets unmixed water, that's when you get a tide line. And when I look at a chart, when I look at a map like this, now I've looked long and hard for some really good tidal front pictures, and I get tide fronts on beaches and lots of tide fronts, but none that the ones we see all the time, which are there's logs and seaweed collecting along a tide front. Okay, this one is also probably much very fresh water and saltier water, so it's got a big density difference. But on the denser side, you can think of this as mixed water, and on the less dense side, it's unmixed water. The mixing at the surface always makes it denser. That's the key point here. And so if this water is denser than this water, when they meet, the dense water subducts underneath the light water. It has to sink underneath it. And anything that's floating on the dense water, like my sweater, piles up at that front. Any seaweed, logs, bubbles that are floating on the dense water, as it subducts under, they get skimmed off along that tidal front. And you get a collection of bubbles, you get a collection of seaweed, you get a collection of logs, sticks, branches, anything that's floating is going to collect along that tide line. And it's the dense side is subducting underneath the light side. The mixed side in the Gulf Islands has recently been somewhere where there's turbulence. That water has come around a point and it's had an eddy, it's had a boil, it's mixed vertically and become dense. Now the tide's slacken off. It's not obvious that it's turbulently mixing right now, but in its recent history, it was mixing vigorously in some turbulent region became denser, has now run into this less dense water, and it's skimming, it's getting all of its flotsam skimmed off, and that's what gives rise to the tide line. In this case, it's just sort of bubbles. And I searched the web for pictures of sort of kelp and sticks that, again, many of you would see almost on a daily basis. You go out there and you'll see a tide line and it's got all this flotsam on it. On one side of that tide line, the water's denser, and on the other side, the water's less dense. On the denser side, it's been recently mixed somewhere, maybe at Race Rocks, maybe through Goat Bay. And on the less dense side, it hasn't experienced that turbulence. It's sort of it's moved somewhere else. And when these two water masses meet, they form a tide line. When I cross the tide line, now I'm in my trawler, my 45-year-old trawler, and I've got the GPS and it's mapping my speed, and I watch as I cross the tide line. It's not obvious to me, even though I'm an oceanographer and I look for it, which side is more dense than the other. It's not visual off. In this one, it's obvious. This is fresher water, clearly like Fraser River water and more salty water. Very often, it's not at all obvious which side is mixed and which side isn't. The material collects, and it collects sort of in the area. It doesn't collect on one side or the other. It's collecting more or less on the fresh side. And then when I cross it, I look at my speed, and my speed almost always changes. It always changes, at least half a knot, maybe quite as much as a knot. Plus a knot to minus, plus a half a knot to minus a half a knot, let's say, 1 knot change. And sometimes it's not obvious whether the fresh water is getting pushed over the dense water, or the fresh water is still, and the dense water is getting pushed against the underwater. Both are probably happening. Because I keep looking, going, oh, I figured it out. And the next time I look across front, no, it's doing something else. And I think that's because sometimes the fresh water is moving over the dense water, and sometimes the dense water is moving underneath the fresh water. All right. Let's carry on with some other interesting things. Eddies and boils. So I'm just going to give you a little bit on current shear. And the only real kayaking I've done some river kayaking, although I do have a little river kayak now for our trawler. I don't have a sea kayak. But obviously shears in currents are tricky areas. They're areas to be very cautious around. And shears can be complicated in place, and if you're going to run into trouble, waves is a separate issue. It could be a whole other talk about waves, but shear zones are really tricky. So here's this map. Again, this is a shear zone up here. It's going to be stronger currents out here and weaker currents here. So along this shear line, this tide line is a shear line. And I've just drawn some examples. As an oceanographer, we would break it down into a little coordinate system. So we have the y-axis and the x-axis. The y-axis would be north, or we'd call that up, and v. The x-axis is also east, and we would call the east component of velocity u. And so if we have a shear zone, like here, we've got currents flowing in this direction here, and it gradually shifts to currents flowing in this direction up here, we would write that as this gradient. It's a change in u. U is going negative, u is going positive, as a function of y. I'm going vertically here. I'm looking at the east-west current, u, as a function of y. All right, so that's how I write that type of shear down. There's two other types of shear which are kind of interesting. This is sort of deformation. This is convergence and divergence. So I'm changing u, but now I'm moving in the x direction. I have strong currents going to weaker currents. When that happens, water must be piling up or subducting underneath. That water can't just disappear. It has to go somewhere. It may not be obvious to me that it's looking a little bit higher, but so it's subducting under. And where I have water that was slower and now speeding up, it must be coming up. I'm replacing this volume from somewhere. It must be from below. When I have to get rid of water, it's got to go down. When I'm adding water, it's got to come up. All right? And that's going to happen around a boil. And I think I've got a picture of his Race Rocks. Sort of a funny picture. I don't know if that's a boil, but it's some turbulence behind Race Rocks there. And then this is actually a picture of some work I was doing in Sampson Narrows, trying to measure the turbulent velocities and currents in Sampson Narrows. And here's the classic, and this is only sort of a side view. If many of you have been out there, you've seen lots of boils. They tend to be somewhat circular, so the water's coming up in some central region, and it looks very calm. And one of the reasons it's calm is that water's pushing all the waves to the side. It's just pushing all those waves to the side. And because the water's moving sort of radially out from the center here, the waves can't get there. They can't get there, and so they all pile up around the edge, and here's that water that's converging. So it must be going down. It's coming up here and going down here. All right? So that's sort of a boil. And again, these are all sort of areas to be aware of what's happening out there. There's shear associated with them. And the shear is at scale of the length of your kayak to even the separation of your paddles. I'm sure some of you have been through these tidal shear zones where literally you put your paddle over here, it's going one direction, you put your paddle over here and it's going another direction. If I go back, let's just go back to this diagram here, this form of shear, and this is vorticity, this is circular, you know if you crossed your kayak across here, your kayak is turning. It's going to turn around like in an eddy here. And if you've ever been caught in an eddy, and I have in a large sailboat, been caught in an eddy and it's hard to get out of. You have to, now in a paddle you want to avoid them and maybe you go in it for fun, but they probably most of the time want to be avoided. The last topic, oh here we're almost there. This is wind against tide and tides when they interact with wind waves. And when the wind and the current are opposed, wind waves can get arrested. That's sort of my oceanography term there. They can get held up, all right, by the current and result in very rough or even standing wave conditions. I think you guys have a name for that. We would call them a standing wave as far as an oceanographer is concerned. This is because the wave energy opposing the current direction gets stalled or completely arrested by the current, and the wave energy then just gets trapped in one area. And this is a classic sort of first-year oceanography question, is what speed of current does it take to arrest a wave? And so this is going to give you a little bit of a lesson here. There are two speeds associated with waves. There's the group speed, which is the speed at which the wave energy is traveling at. And then there's the phase speed, which is the speed that the crest of the wave travels at. And they're not the same. The crest wave travels twice as fast as the group speed. The group speed is the energy we need to arrest. That's the energy we need to stop the wave energy from advancing. And it's already half of the phase speed. Both are related to the square root of the wavelength. Interesting enough, the speed of the wave depends on the wavelength, not the wave amplitude. You can have a very short, steep wave that's traveling slowly. You have a very long but low amplitude wave, it's going to travel very fast. So the difference between wave speed from a long wave to a short wave, that's called dispersion. And we've actually done lots of experience where we monitor a very large storm in the Southern Ocean that generates all the wavelengths. The long waves will reach Alaska up to a week ahead of the short waves from that single storm event in the Southern Ocean. So the long waves get way ahead of the short waves. Surfers know this around the world. They'll track a storm and they'll map when the long waves will arrive first and then the smaller waves. If they want the large waves, they arrive at the west shore of Hawaii sooner than somebody who wants the smaller waves. So let's look at a diagram of what's happening here. This is how wave energy travels in the ocean. Now there's lots of groups happening all the time, moving in many, many different directions, but trust me, they are all in groups. What we're seeing here, if you follow the crest, the peak of any one wave, it appears to start at the back of the group and die at the front of the group. It's traveling faster than the group speed. The group speed is the at which the whole group travel. That's half the speed at which any one particular wave is traveling through the group. You can see groups of as few as 2 or 3 waves. A wake from a boat travels out from the boat, the path of the boat, at the group speed, but within that group, waves seem to appear at the back and die at the front, appear at the back, die at the front, appear at the back. So the phase speed is propagating through. Now when you're on the water and you're seeing wind waves, and the waves that are close to you, you're really responding to the phase speed. There's a wave right there, and how fast is it coming to you? But it's the group speed that is most important. When I have a current that opposes that wave energy, all right, it starts to slow down the group. So this group is going a little bit slower, and it's compressing these waves. The wavelength is compressing. And because the speed is proportional to the square root of the wavelength, the whole packet starts to slow down. Not only is the water now moving in the opposite direction, so you can imagine the water mass is now moving, and all I have to, and so the waves aren't advancing as fast. I only have to move the water half the phase speed because the group speed is half of the phase speed. And as the wave gets compressed, it starts slowing down and slowing down itself. And eventually, at some point, I get the wave energy is arrested by the current, and it turns out that that current speed is only a quarter of the wave speed. I get half because it's the group energy I need to stop, and I get another half because I shrink the wavelength down and the wave slows down. And so I get this standing wave. The wind's blowing. Waves behind it let's say we've got a localized current. And it's strong enough here to arrest the waves, but it's not strong enough to arrest this group. What's going to happen? This group comes along and it piles onto this group. And it keeps coming in. This group of energy steep keeps coming in and it gets rested here, and this group of waves gets bigger and bigger and bigger. And you eventually get standing waves here that look huge compared to the surrounding area. The opposite thing happens when the wind and the waves are with the current. They get spread out, they get longer wavelength, they're both advected away quickly, and their wavelength increases, so they travel faster. So when wind is with the currents, it looks flat calm. The waves just take off. And when the wind is against the current, they seem to slow down, and then you get these standing waves. So you get patterns of slick, no waves, even though the wind may not be very strong. It's the piling up of group after group after group at this place where they're getting arrested that gives rise to what it looks like. There's strange. There's no waves anywhere else, but all of a sudden there's all these waves in this one area. Okay, and I managed to pull this figure off of, I pulled this figure off of the same website that is now probably in his book. And I looked I looked on the internet, really couldn't find anything, but I did find this one. Now, we can look at this picture and there's a lot we can tell just from right here. First of all, the sails are billowing. It looks like the wind is blowing from over here to down here. It's hard. I think this is sort of washed behind the waves. The waves, I think, are propagating in the direction of the wind. The wind is driving the waves. So the waves are propagating in this direction. There must be a very strong current in this region that is posing those and building them up almost into standing breaking waves. Not far away, there's no waves. A little bit further, there's waves. No waves, waves. I suspect the wind may be quite uniform over this whole region. We've got a tidal jet pushing against the wind here, weaker currents here. A tidal jet pushing against the wind here, weaker currents, stronger currents. So without any sort of other knowledge, I've got strong currents here, weaker currents here, strong currents here, weaker currents here. Again, you might want to go in here and have a lot of fun. You can find a standing wave and you might think, oh, it's going to be kind of fun. You might want to avoid that. So look for these areas. This is going to be, depending on the direction, if you're traveling in this direction, that's where the current is flowing in this direction, probably. The winds are going this way. The current's going this direction. So if you're going with the current, you may want to stay on the edge of this and try to get boosted along. If you want to avoid the waves, you're traveling out here, but you're not going to have such strong currents traveling in that direction. I think I've exhausted everyone here and my time. Thank you very much for your patience and sticking around.
Questions?
Yeah, I don't mind if you have to leave and get up and go, that's fine. But if you do want to stick around.
Questions?
Quick one. The charts the current charts that you showed us, at what depth are those currents?
Very good question. Some oceanographic models will simulate the currents at different depths. Almost all tidal models don't do that. It's a depth average current. So in the current vectors that I show there, it's depth averaged. And in coastal regions or in shallow water, that's good enough. The surface water and the deep water are more or less traveling the same speed. In deep water like Harrow Strait, there's going to be some shear. There's going to be stronger or weaker currents at the surface than there is at the bottom. But almost all tidal models are depth average currents. So when you read the tide tables, they're almost always for current stations in constricted shallow passages, where that current represents the whole current at all depths. So it's as good as being the surface. In deeper water, it's less so. It's the depth average currents. So for the vectors that I was showing there in the current atlas, it's the same in Pat Crean's current atlas, the one you could, if you still have it. I don't know if they still sell it. I think you can download it. There was a copy here on the bench. You can now download the original current atlas. And on my website, if you download the updated current atlas that I'm starting to generate, it puts a link to the original one as well. And those are, all tidal models are almost always depth averaged. Okay? Yes?
I have a question. I've always wondered why Baines Channel is 15 minutes ahead of Race Rock's current, whether it's an ebb or a flood.
Okay.
And in addition to that, as if that's not perplexing, but maybe it isn't, given what you said about turbulence, in Enterprise Channel, not very far away, somebody I know who lives near there says it changes an hour ahead of Baines Channel.
I've heard that. I just even heard that this evening, and I was not aware of that big difference. Again, Race Passage is deeper than Enterprise Channel, so as the water gets deeper, it will retard how quickly it turns. The shallower the water and the more turbulent, the quicker it will respond to a change in the surface slope. So I suspect what's happening is that in Enterprise Channel in particular, it's turbulent and shallow enough that as soon as that slope pops the other way, it starts responding and flowing. And even though I have typically thought about that happens really quickly at Race Passage, it's deep enough and has enough momentum behind it that this water rolls uphill a little bit before it turns around. I've tried to make measurements in both Baines Sound and Race Passage, and it's just a nightmare. You can't get anything vertical up or down. It just, everything's just flying all over the place. So from an oceanographer, I did get one. We were working in Race Passage, trying to make some measurements there, and we were struggling. We couldn't get anything to stay down or put down or get through the water column. And we were looking at the chart, and there's a little nodule just sort of towards Victoria, maybe 5 or 10 kilometers from Race Rocks. And I was with a really good oceanographer, Chris Garrett, and we looked at that, and I said, Chris, there's a bump. There's a bump over there, so like Peter Sellers and the Pink Panther. And we did an entire study around our bump, just to the east of Race Passage, where the currents were still strong, but not as crazy as they are in Race Passage. But that's very interesting, that Enterprise is up to an hour ahead of... So if that's true, Enterprise Channel changes an hour before Race Passage, and Race Passage changes an hour before Juan de Fuca east. So Enterprise Channel is changing as much as 2 hours before the deep water. And then it would be similar times to the deep water in Harrow Strait, which is also 300 meters deep. So that water's got to really roll uphill for a couple of hours before it changes. So I don't doubt that. That's interesting. Don't hesitate to email me, or we can break up now and if there's any cookies left. Yeah, sure.
You used a lot of new terms to me, but one of them,
Yep.
the most recent slide, so I can remember it, is that tidal jet.
Yeah.
Now, I'm presuming that's just a discontinuity in the speed that's...
Yeah, tidal jet, I mean it's some sort of lateral stream that's being compressed. Let's say it's going through a channel. So it's wide water and it's coming through a narrow channel. Dodd Narrows is a good example of a tidal jet. It's just, and now around that trial island there's going to be a tidal stream. Now it's not constricted laterally like a channel, but it's the tide's hitting Trial Island, running around it, and there's going to be a narrow jet that probably 100 meters wide or so, where the currents are stronger than they are either side of it. One side may be in the back eddy, so much weaker, and as you go into deep water, a little bit weaker again, and you've got the strongest currents going around that headland. And so that's what I'm referring to. There are other terms like a tidal stream, but one could argue that the entire Juan de Fuca Strait is a tidal stream. So we want to distinguish sort of a jet from a tidal stream, so that's why I might want to use those two different terms. Yeah.
So the models that you use, say for your tide atlas,
Yep.
Do they become invalid over time? I mean, is there a drift compared to...
Really good question. The Canadian Hydrographic Service continues to make measurements, very seldom of currents, but mostly of tidal heights. And they will analyze the new measurements and add it to their archive, and they do what's called a harmonic analysis, and they look for the harmonics that are in tides, and you break down into tidal analysis into maybe as many as 80 different tidal constituents, all the funny frequencies. And it's like Fourier analysis, but we pick very specific frequencies. And so you get a harmonic, which is the amplitude and phase of each of those little constituents. And that allows you, once you have the harmonics, and you can do a fairly good job. My tidal model only has the main 8 constituents. Most of the tidal apps will have maybe 30 or 40 in their harmonic analysis, but the top 8 are doing maybe 80% of the tides. And those harmonics won't change very much over a period of even hundreds of years. So in my tidal model, I'm fairly confident I can predict out. Now, I've compared my tidal model to the Canadian hydrographic tides again, and there's subtle differences in phasing. We're talking about 10, 15 minutes here and there, but generally they're fairly good. And so the tidal harmonics in apps and that you can get on the phone, and most of the Navionics, for example, has tide stations in there, those are going to be fairly good for decades, certainly our lifetime. The average age in this room doesn't need to worry about that. Sorry to say that, but there you go. Yes?
So if you're saying we don't have to worry about the tides changing too much, but you say the current atlas is outdated.
Well, the old current atlas is fine, but it has fairly coarse resolution. And it can only just resolve some of the largest features that are out there. There is an eddy behind, I don't know if I could draw this, there's an eddy behind Discovery Island. So you get the flood tide goes around the lighthouse there, and it funnels over to Harrow Strait on the San Juan Island side, and you get a back eddy behind Discovery Island, where it's actually under a flood tide heading southward along the backside of Discovery Island there. Under an ebb tide, you also get the ebb tide pushes that way too, and you get a big eddy behind Discovery Island. The Pat Crean model, the early one from the late 70s, just about resolves that eddy. In my model, I've got like 30 points that are showing that eddy building up there. So it's higher resolution, and it allows me to get in and see and as a result, by being higher resolution, I can see a little bit more in the shear. The timing and the shear is going to be very similar, on the large scale. But if you want to get to smaller scale, the new atlas is there. I'm giving it away. I'm doing it because I have it. And it just seems a shame to be using a tidal model that was coarse from 50 years ago when I have a newer one. So I'm just putting it out there. I wouldn't say the information in the old atlas is wrong. I'm just providing it with a higher resolution. And now I'm expanding the region. The old atlas only covered the Gulf Islands and San Juan, and I'm going to put out one with 5 different volumes. Unfortunately, the files are large. You can imagine I've got, in any one region, I've broken, not only in the original tidal as you had 1 page for the entire San Juan and Gulf Islands. My model, like you see the resolution you have around Oak Bay. If I zoomed out to do that, you wouldn't have any ability to read what's happening in Oak Bay. So I've subdivided each volume into 9 subsections, and then each map within each subsection there are like 43 maps. So in each volume there's going to be 300 or 400 pages of maps, and there's going to be 5 volumes. So it's a big volume, but I'm letting the computer do all the work. Yes.
My brain hurts a lot right now, and
I hope there were some things that fill gaps, though. Yeah.
And I probably won't sleep, but I want to thank you very much.
You're very welcome. Very welcome.
We're going to have to cut it short because we have to be out of here, but
Yeah.
I just wanted to mention, Richard, that the next time I get caught in standing whitewater, I'm trying like hell not to flip over. I'm gonna remember the formula you put up there. I want to present you, this is the much sought after, seldom seen
Thank you.
mug from Siska, and it's good for hot and cold water, and it floats in any current. So,
Thank you very much.
Richard, thank you.
Thank you.
Please stack your chairs where you got them, 3 high, and they get upset if they're not done right.
The presentation is on the laptop here. You can get it off this laptop or email me and I can send you the presentation.
Thank you for making it.
Good night. Drive safe. See you next month.